Pratik Hiremath from Yuken, India. He's going to talk about leveraging shape memory effect in hydraulic systems with thermo-responsive sealing and adaptive cooling. A brief biography of Mr. Pratik. Pratik received his BTech degree in mechanical engineering from Shivaji University, Maharashtra. He is deeply passionate about science and its transformative power. During his engineering, he has worked on several development projects. He has a registered patent on his work regarding intelligent battery cooling systems in EVs. With 3.5 years of professional experience in the hydraulic industry, he has worked on real-world engineering challenges in the domains of system design, product development, and analysis. To him, science is more than formulas and experiments. It is an art, a way of perceiving the world, and at its core, a spiritual pursuit. It teaches to observe, question, and evolve constantly. Over to you, Pratik.
Right. Audible properly? Yeah. Namaste, everyone. Very good morning. Thank you so much. Glad that I could present this over to you. So, the topic says leveraging shape memory effect in hydraulic systems with thermo-responsive sealing and adaptive cooling. It's a fairly simple, straightforward topic. I'd be talking mostly regarding the thermo-responsive sealing, and the end would be a little discussion on adaptive cooling. So, what was the idea all about? You can see this picture showing some blue traces indicating leakage under the UV light. The aim is to reduce this leakage and make it something like this, which is with no blue traces, especially when it comes to systems at higher temperature. So we are talking about leakages at higher temperature in essence. This entire presentation would be covered in 4 sections: ABCD, why and what, how, proof of concept, conclusion. Why and what is the initial motivation, why is this an issue, and what happens because of which this issue is causing, and then how I have tried to mitigate it. Then C and D following. A section says hydraulics at higher temperature seal behavior. So since we are talking about leakages, let's talk about seals. An introduction to the seals. What are seals in essence? You can see that blue circular ring is a seal, which we also call as O-ring. So seals, O-rings are elastomeric compounds which doesn't allow the oil or gas to pass through them. Simple as that. How do they work? Basically, they are placed in some grooves which separate the oil and they kind of block the oil or air so that it is not passed through them. Basic mechanism of any seal, as you can see. Right? Fine. Effect of temperature on the seals. All rubber is subjected to deterioration at high temperatures. The first effect of increased temperature is to soften the compound. Says not me, says Parker. And here are some graphs which tell you, which are in support of the same statement, telling the drop in the hardness as the temperature increases. As you can see, the negative slope of the graph. What can happen if seals become soft? It is becoming soft, fine. What is the issue with that? Oil pressure deforms the O-ring and can lead to something called as O-ring nibbing. If such an O-ring is placed in our groove, that could lead to what is called as micropores. And these micropores are the sites where the oil can leak through. Let me explain this to you with this illustration. You can see the O-ring placed in its groove. A normal O-ring would deform a little bit, but its hardness and its Young's modulus is enough to sustain the oil pressure. However, a softened O-ring might not do so well. The oil might still pass through it, deforming it even further. In some worst cases, we can also have this pitting thing going on called by the name micropores, as I had shown before. And that could be even worse, could lead to some catastrophic failures. One more effect of increased temperature is, a softer seal deforms relatively easily. Then the deformation opens up the micro clearance spots, and eventually the oil leakage can happen through these spots, as you can see right here. Right now, one more effect that temperature brings in is the reduction in oil viscosity, as you can see with the negative graph here as well. So all in all, at high temperatures, O-ring becoming soft and oil viscosity reducing together brings in what? Leakage, right? As a conclusion, I would like to tell finally that increase in temperature leads to increase in oil leakage, very evident, very obvious to everyone here. So what are the current conventional ways to mitigate this oil leakage? Oil leakage is definitely a problem. What are the current ways that have been done to mitigate this oil leakage? Here are some of the ways. Improved seals, be it ACM, HNBR, Y-turn seals. Installing efficient cooling systems. Don't allow the oil to heat itself. Preventive maintenance and replacement. O-rings needs to be replaced once they deteriorate. Fine with this, the world is going on well. However, still the reduction in hardness is an issue which is an inherent property of seal that still happens here as shown in the graph, HNBR, FKM, ACM. The other processes are secondary techniques, they're not causing, helping to do anything with root cause. Fine, at this time, what we are trying to propose? We are trying to propose what is called as a thermo-responsive seal. What is this thermo-responsive seal? The idea is to make the seal compensate for the excess deformation due to loss of hardness at higher temperatures. How do we do that? Let's say this is the original O-ring size. Now due to softening, it reduces and becomes a soft O-ring with a less size. We can see there is a radial clearance present. What if we could push that O-ring back to its original place by exerting some active force? Would it not be nice if you could get this active outward force on the seals? It would just place it back to its original place. Please look at the follow-up video. If you observe well, you can see something is expanding. What is this something? I'll talk about it now. Well, if you take nickel, mix it with certain proportions of titanium, and convert it into a BCC nickel titanium structure, what we get is what can do this. It can undeform and come back to a preset shape when subjected to temperature or electricity. This is called as shape memory effect. We had some presenters from IIT Indore who had already talked enough about this. So I'll just take you through quickly. Now this nitinol structure is also known by the name shape memory alloy. Yeah. So the idea is the original shape, if we deform it mechanically, it converts to twinned and detwinned martensite structures, and then we can recover it again, taking it to austenitic state. The physics of this is very, very interesting. I would be glad to have a discussion offline on the physics behind this. It's a very interesting topic to discuss. So this is about SMA. We all know about it. And the ring that I had shown in the previous video is obviously was SMA, and I was just increasing the temperature. The actuation range can be varied based on the alloy doping percentages of nickel titanium. And there are various other SMAs available, be it ferrous-based or copper-based. So in essence, a temperature sensor and an actuator is what this shape memory alloy is. It's an actuator, hence it can apply an active outward force. And if SMA is incorporated in seals, it could essentially become an active thermo-response seal. So let's incorporate this I've taken a valve cross-section, and as you can see, there is an SMA strip and an SMA ring just placed behind or just adjacent to the O-ring as a support. Now, what can this do? This can actually expand when the set temperature is reached. So this is the unactuated state of the shape memory alloy and the O-ring. In the video, you can observe that the ring, SMA ring, is trying to deform the O-ring outwards. I've made a cut on the O-ring so that you can see the slit getting separated. And that's how we get the active outward force, as I was mentioning before. This is the entire essence of the project. So, I had to do some calculations. I cannot just randomly take any SMA, place it in the ring form, and just make sure, just be ensured and happy that it will work well. I had to go through some calculations, which are very obvious, important. First, I had calculated the amount of softness that the O-ring could undergo due to temperature rise. I had taken some temperature reference at 75 degrees Celsius. Then the follow-up would be the deformation that can happen due to this softness, the amount of force that is required by the SMA, and the wire selection was the follow-up thing. The details about the calculations are right here. I have used all the hyperelastic models. No linearity involved here, no Hooke's law. We have used new Hookean models. Some experimental, so about 18.2 Newton force is what is required by the SMA to push the O-ring outwards back to its original shape. I've talked about using SMA here. We are using it with hydraulic oils. We cannot use it just like that. We have to ensure that it is compatible with hydraulic oils. Safe and compatible with hydraulic oils, excellent corrosion and wear resistance is what these studies say about MSDS regarding nitinol. Some design iterations that we have gone through while incorporating SMA. We have made a slit in the valve to incorporate SMA ring, and then we had placed O-ring after that. Another design was made where a cut was made in the O-ring groove, O-ring itself, so that we can accommodate SMA ring as shown here. We have also gone through an idea of reinforced SMA inside the O-ring. That could be a retrofit O-ring. We can just place it on the go. Proof of concept, as I've shown, we have a visual expansion happening right here. We have also placed that in the groove of a valve. By rise in temperature, we could see at no load state, no pressure state of 1.5 mm, expansion of the O-ring was observed. And here are some findings. Austenite start, austenite finish, when was martensite start temperature. We observed a hysteresis of 5 degrees Celsius. However, thermal hysteresis is of benefit to us in this case. More information on this we can discuss offline. Yeah, fine. So this was all about the sealings. Since I have made a initial discussion on SMA, I would like to use this setup as a way to talk about something else other than the seals. I would like to talk about adaptive cooling as well, where we can utilize this shape memory effect. So leveraging shape memory effect in adaptive cooling. What is the idea behind this? Industrial applications with intermittent duty cycles do not require continuous cooling. However, we see that heat exchangers are already always installed, and the return line oil has to go through the heat exchangers all the time. They add to the pressure drop as well. So can we develop a system which sends the oil towards the cooler only when required? That was the idea behind this. Now, what can SMA offer at such case? SMA can offer us a spring which can elongate at higher temperature, just like that. So this spring is now deforming based on delta T, based on temperature. If we could place this spring inside the poppet instead of the conventional spring, what we could get is a valve which would be now responsive to temperature. And such a setup can be made where we can maneuver the oil based on the temperature difference, based on the temperature initiation. What I call this is what I like to introduce now. Introducing SMA-based thermal relief valve. The idea is very simple here.
Pratik, you have another minute
Yeah,
to
sure.
conclude. Thanks.
So this is the entire system of the valve body. You can see there are two passages, one going bypassing the cooler directly to the reservoir, and one passage goes to the cooler. Usual conditions, the oil would just pass, open up the poppet, and go towards the reservoir when the cooling is not required. However, when the cooling is required, when the temperature is reached, the poppet would just go down because the SMA has expanded enough, and the oil would then go towards the cooler. It's the all idea of thermal relief valve. So conclusions from this. The chances of leakage through O-ring increases at higher temperatures due to softening of O-ring. SMAs are the entities that respond to certain temperature by showing deformation and force. This is an active leakage compensation technique, and the same thing can be used to leverage in the thermal relief valve. Advantages: large actuation force, excellent thermal response, multiple actuation temperatures possible, high corrosion and wear resistance, chemically inert, compact and light. Important disadvantages are also there. Very careful in designing of SMA ring, and it is a complex process, complex behavior that should be done very well, properly. Some key comparisons between different actuators, we can discuss this later as well. What would be the future work? Encouraging the future work. Performing on-field tests is what we need to do henceforth. It is in very infant early stage. We need to do multiple tests before getting it on the field. So that was all from my side. Dhanyavad. Thank you so much.
Thank you, Mr. Pratik, for your nice presentation. One query, that is here you are considering the shape regaining of the seal using SME in the axial direction, sorry, in the radial direction. Now, when the seal is translating inside any barrel hole or maybe inside any manifold, so the axial shape distortion will also be there. So have you done any experiment or through simulation whether the shape regaining can be done in the axial direction as well?
Yeah, so as of now, we have done only considering the radial deformations in a very fabricated manner, just radial things. We have not gone through all the possibilities that could happen, as you rightly mentioned. But yeah, we could definitely think on that, and we could definitely do that as well.
Okay. Over to the audience.
Hello, sir.
Yeah.
Sir, here. First.
Yes, sir.
So I'm Arpit from IIT Indore,
Hi.
and we are like very happy to see the real-time application of how you're using the shape memory alloy.
Yeah, same
And
here, same.
yeah.
I was happy to.
So
Yeah.
I just wanted to understand, like, the idea is that when the O-ring gets softens, then effectively you can use it. So if we are installing it beforehand only, so how we are going to utilize the O-ring effect at the same time utilizing the shape memory effect?
Yeah, right. So that is why we had made a groove on the valve which would accommodate SMA. At lower temperatures, SMA is as if that it doesn't exist there. It is just placing inside that groove. So no use of SMA at that point. Only when the temperature is reached, at that time it would expand outwards, expanding outside the boundary of its groove, and then pushing the O-ring. So without the temperature reach, it is as if that nothing exists there. It is just sitting in its groove. So multiple design iterations can be done to think on what all possible problems could arise with this. Definitely can be taken into consideration.
Hi. Thank you very much. It's a very nice presentation. So I have one suggestion. Instead of a shape memory alloy, can we use a shape memory alloy polymer?
Yeah, polymers are weak in nature. They
Okay.
are susceptible to, they cannot exert higher forces. In fact, I've mentioned that in the end slide as well. Since we work at very high industrial pressures, so shape memory polymer. Force output is moderate, as you can see here. Not as much as what SMA could do, because it is polymer after all. It is not an elastomer, so that was the thing. But again, we can do some research on that. We can definitely consider that as well.
Yeah, so that you don't need to make two different components. It becomes a single component.
Yeah.
Thank you.
Hi, sir. How?
Sorry, can you use the mic?
When you reinforce, how you consider thermal boundary condition? What are the thermal boundaries you have considered?
Yeah, so
Can you please brief? It is a little bit more elaborative.
the reinforcement has to be done with considering a lot of things. One is the temperature sensing. Temperature sensing has to be done very well so that the SMA could sense the temperature through the elastomeric O-rings. Maybe that was the point that you were asking. So yeah, it has to be placed in such a way that the temperature difference can be in contact with the SMA. Maybe we can have an offset kind of SMA which is inside the O-ring. So multiple issues might appear as we are going through that. While in the fabrication stage also. So this was just a concept that I had put forth. That's why I had just shown a CAD model. We could not do anything about that. So there's just a possibility that can happen. Yeah. Thank you. Yeah.
Thank you.
Yeah.
I have a question on.
Yeah. Yes.
So you said at high temperature, let's say from 50 to 80 or 110, your shape goes outward. What about the minus 40 means? In those cases, does it come down or it stays there? So what is the case?
The reason why we are doing this is because O-ring is getting soft. That softening is happening at high temperature only. So we don't need to worry about low temperatures. But if we want an actuation at low temperature for certain other applications, SMA can do that as well. There is a wide range of actuation temperatures. So we can incorporate an SMA which could actuate at minus 4 degrees Celsius also.
No, not about actuation. Does it come in a compression set? I mean, does it reduce the shape of SMA in that case?
No. Compression set in the O-ring happens at higher temperatures when the copolymerization, the interlinks are broken, and that's when it reaches to this hardness thing. At low temperatures, interpolymers are still intact. It gets hardened because of the drop in the Young's modulus. So I don't think it will have any force in the SMA as such.
Okay. Thank you very much. Can we take the next questions after? Last question? Okay, last question.
Hi. You mentioned about a terminology called thermal response. I'm here.
Yes, sir, yes.
With this adaptive cooling that you mentioned, when you say thermal relief valve, there are a lot of factors that is influencing the temperature on it.
Right.
Because you are keeping the spring between a poppet and a cap plug, correct?
Right.
So there is an external environmental temperature affecting the plug surface, and the fluid temperature will be directly acting upon the poppet.
Right.
So my spring is in between these two components. So how would you rate that it has a good thermal response? Because there is a lot of difference in the input for the SMA.
Yeah, so the oil would get heated up. The
Correct.
heated oil would be sensed by the spring.
Right, sir.
That would be it. We think would not be in position to consider the ambient temperature as such. If the oil temperature itself is exceeding, and then we want to send it to cooler, that is all about it. The oil temperature would be sensed by the spring, and it would actuate.
But when you say the thermal relief valve, when you showed a CAD model,
Yep.
there is no direct contact between the oil that is heated up and the
understood.
spring.
Understood. So,
Right.
yeah.
Pratik,
Yeah.
let me. Sir, just answering that question.
Yes, sir.
One, it was a POC.
Okay.
Two, to answer your question more specifically, conduction is more or less a linear phenomena.
Correct.
So, like he mentioned for many of the other cases, there would be a design iteration, and we would be mapping the linear phenomena of how heat would transfer through the poppet. or through that thickness of material, that would be factored in.
Right, that's true, sir. Because every material has its own thermal conductivity
Absolutely.
coefficient.
What is going for us is the fact that it is a linear phenomena and you can account for it and
Right.
work with that.
Right, I'm just curious on that note. Thank you, sir.
Yeah.
Thank you very much. Other
by,
questions? Okay.
by the way, the wall that we had used here has a pilot line which comes from the P port. So oil is directly actually in contact with the spring. It is not shown here, but there is a pilot line drilled towards the spring. So that line is always going to the spring. It will be filled with the oil. And also the conduction plays a role there.
Okay. Thank you very much.
Before ending, I would like to have just a minute to thank few people without whom this would have not been possible. Suresh Kannan sir is sitting here, who initiated all of this. And he is one of the prime reasons that I'm standing here and presenting in front of you. Also, Hemant sir is here, who was the guide throughout the project. And these two are into corporate businesses. I only see them as scientists. So they inspire me a lot. Thank you so much for being there. And yes, and also very happy to present this on a wonderful day where Mr. Blaise Pascal was born, great scientist, inspiring figure, definitely. And a salute from my side to scientists like him, who has inspired people like me to work in the research. Thank you so much.